Can you hear me?
Can you hear me?
Me? Why am I muted?
People online. People online, can you hear me? Okay.
There it goes.
So you can hear me, right? Oh. Sorry for the late. The podium computers aren't working, so we blame WSU again. Yeah. Okay, so it's February 6th, CS797K, Advanced Topics in Data Storage. It's 11 a.m. So we just go through errata, RAID, overhead. So Professor Wilner, he pointed out he has something to change in the yesterday's slide from the last lecture slides. So it's not like something wrong in the previous slides, but the people now are using something different. So RAID overhead should be expressed as numbers of parity drives divided by numbers of data drives. So if you have one parity bit, one parity drive and 4 data drives, it should be like 1/4. So 0.25. So that's how we write overhead. So total number of drives divided by number of total drives, we said. So that's how they used to calculate. But now even the chat GPT is showing number of parity drives divided by number of data drives. So we just want to change that. Slow. So, okay. So RAID 1 mirroring, disk 0 and disk 1, write 2 copies of everything performance. Overhead would be 2x, 1 parity drive, 1 data drive, 1/1. So it's 100%. Yeah, we changed it. So 1 0. So how many parity drives here? I guess no. 2 to 1. Yes. RAID 3. It's 1/n, not n plus 1/n. So it's parity by data drives. That's it. Simple. Me share RAID DP. Share. So I'll try my best to explain clearly for you. If the podium computers are working, we could look at the camera, but now my camera is showing flipped. My camera is flipped. Let's see how this goes. So it's RAID RDP or RAID DP, RAID diagonal parity, or RAID, what's R? R is row diagonal parity. Yep, yeah, okay. So we generally call it RAID DP. It's the diagonal parity. So if you know how to change the numbers from binary to decimal or hexadecimal. And if you know how to calculate the parity, then it's an easy lecture for you. So let's see where we are. We are going to discuss diagonal parity today. So Reed-Solomon coding, it's the latter lectures. We are going to discuss Reed-Solomon coding in 2 lectures because it's a little complex topic, or it's easy topic. Yeah. So we have finished our Hamming code. We have finished basic RAID, and we are going to discuss RAID RDP today. So RAID 4, things to note. Disk blocks are fixed size blocks, usually 512 KB, 512B or 4 KB and so on. So what are disk blocks? So this is a disk block, disk 0, disk 1, disk 2, disk 3. So these are the disk blocks. And we saw what are stripes in the last lecture. So the horizontal one is a stripe. How many stripes we have here in this diagram? Yeah, it's 5. It's 5. Yeah, it's 4. 4 stripes. This is 1 stripe, second, 3, and 4. We have 4 stripes and we have 3 disks. So this is about stripes and disks. So each disk block is a fixed size. Example 512B or 4KB. It's changed now. It's not like the old one. So we have increased the sizes. We may have decreased the sizes as well for the Word documents. Yeah, so it's a stripe. A1, A2, A3, AP is a stripe. B1, B2, B3, BP is a stripe. So these are the stripes. Sorry. Segments, yeah, and segments. So each one is a segment. Okay, so A1, B1, or C2. So these are called segments. Okay, so A1, B2, C1 are typically multi-sector segments. Segment size is configurable 64 KB, 8 KB, 256 KB. So we can configure the segment sizes. So for now, example, yesterday we gave the example of movies. So each segment is what we say. Yeah, yeah. So these are the segment sizes. So we can configure the bottom line is we can configure the sizes for the segments. Yeah. So best segment size maximizes single segment full stripe input output. Yeah. And right for example. So here the block size is 1 byte. It's all integers we have. So the block size is 1 byte. Segment size is 1 byte. Fails drive by zeroing it. So we are failing a drive by zeroing it. Yeah. So each segment is 1 byte. So how many segments we have here? 5, right? 1, 2, 3, 4, 5. 5 segments. So we have 5 segments. So each segment is 1 byte. So how many total bytes we have? 5 segments of 5 bytes, right? Total, it's 30 for the matrix. So segment size is 1 byte. We'll fail a drive by zeroing it. We have failed this drive 2. No error checking. See, or we could just show the IPYNB file now, I guess. RAID 4. Very briefly here. RAID 4 example. I can show you the IPYNB file now. Oops. This is good. So this is the RAID 4 IPYNB file we have. This is the one we have, right? Yeah. We are defining a dump drives. This is the definition. If we run this, we won't have any output because it's a definition. We are going to use the definition later on. And here we're giving num drives as the length of drives. Header. Yeah, this is just for printing, yes. So dump drives dot doc, dump drives question mark. So this just shows the signature and where the file is in the location. So it's in this location when we ran that one. And this is the type. And if we go here, it's a definition to generate parity with the number of drives we input. Yeah. So here, the range from 0 to number of blocks, the blocks, we have discussed what the blocks are now. So what's -1? So what's -1 in Python do? So it's basically a matrix. So what does the first one and second one represent here in the matrix for Python? So the first one is rows and the second one is column, right? Rows and columns. So what does the matrix have? Rows and columns. So what's -1? So if we have like 2, so that's the second row, right? So what's -1 here? Yeah. So last one, -1. -2 means last but one, and so on. So this is how we are updating the drives by using XR with the same thing with the drives DB, and we're just printing it if B is 0. So this is a simple code. You can play around with the code. So this is RAID for illustration. So this is the drum drives we have. This is the drive we have, and we haven't updated anything for parity yet. We can just XOR the things and get the parity, right? So this is how we generate it. We're just XORing it. So generate parity drives, dump drives. So generate P of drives. We have generate P here, right there. Yeah. What we're doing here, we're just XORing the things and we're getting the parity, last parity here. So we're XORing C738 and we're getting a parity bit. So that's what this code explains everything. And rebuild drive. So if we are failing a drive, see here, we are failing a drive. So how to reconstruct this one? How to reconstruct this things, this segment right there? So we'll XOR the things we have in this row. We'll XOR C38C and we'll get 0 back. I mean, we'll get this segment back. Yeah. So this is how we rebuild. Just go through the definition we just written, rebuild underscore drive. We're just XORing things in this. So there's nothing complicated in the what we say in the definition. So it's just the XORing things again. Yes, we're just rebuilding the things. That's it. So this is how this RAID for IPython file went. So I'll just where we have posted it in Blackboard. You can just go there and take a look at what's there in there. And block size. So that is the thing with a screenshot right there. So we have explained this thing. So now RAID DP stripes. So how does RAID 4 work? We'll just it's the simple numbers. It's not a hexadecimal, so it's numbers. So if you want hexadecimal code for 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 0, 1. Okay, if you know how to build that. 3 plus 1 plus 2 plus 3, that's 9. So that's how a simple RAID 4 works. We'll just extend some work from RAID 4 to get diagonal parities right there on the right side. This is the stripe. I mean, this is the diagonal thing. We'll have the dedicated diagonal parity column in the RAID for the diagonal parity drives. Okay. So how do we calculate that? So we'll calculate the diagonal stripe we have. We'll XOR the things. XORing in normal number is nothing but 1 plus 2 plus 2 plus 7. It's 12. So we'll just keep it. So which stripe do we need to take for the diagonal parity? Which stripes? Because you can also take this stripe. You can also take like this stripe. You can take this stripe. So that's the set of rules that was given by the manufacturer at the time they manufacture. Okay, that's the set of rules they give. So let's discuss our X RAID DP extent. So this is how we have built our RAID DP. So that's the thing we have stolen from NetApp. So that's the manufacturers. Those are the manufacturers. They have programmed this thing. So you see the color. So this color is one stripe. So this is how they have given the stripes, and they have a logic for this. And this is not a diagonal stripe. Okay. Let's do you have any idea why they haven't given this stripe? Because every stripe has 4 elements in that. 3 plus 1 plus 1 plus 2, it's 7. 1 plus 2 plus 2 plus 7, it's 12. 2 plus 1 plus 8 plus 1, that's 12. 3 plus 5 plus 2 plus 1, that's 11. So we have another diagonal parity, which we haven't included in here, 1 plus 3 plus 3 plus 9. So that could be another parity. I mean, that could be another diagonal parity, right? So do you have any idea why they haven't considered these things with the to calculate the diagonal parity? Let's see. Let's see. So these are the data bits, data drives. D0, D1, D2, D3. We have 4 data drives, and we have 1 parity drive, and we have 1 diagonal parity drive. So you now know how to calculate parity drives and diagonal parity drives, right? Any question in calculating parities and diagonal parity drives? It's simple. Just add these numbers, you get this one. Just add these colors, you will get the diagonal parity, right? That's simple. So yep. So how have they given this diagonal parity? How did I can't use the board. Online people can't see that. So yeah, next, yeah, okay. So how did they given these diagonal things? So it's simple. They have a formula here. Diagonal stripe equal to D minus B. That's the data bit. B is the oh, drive block or segment. Yes. So for example, we have DS0 here, D0 here. So this is the block. This is the drive. So block 0, drive 0. Block 0, drive 1. Block 0, drive 2. That's like the matrix. Block 0, drive 3. Or block 1, drive 0. Block 2, drive 1, and so on, so forth. Okay. So D minus B. For example, if we take this element right there, it's D0, D0, B0. So 0 minus 0, it's 0. And again, let's take this one here. It's B1, D1. So 1 minus 1, it's 0 again. So it's 0 diagonal parity. And again, what's this one? This is D2, B2, right? It's B2, it's D2. So 2 minus 2, it's 0 again. Yeah. And let's take this one. It's B3, right? And D3. 3 minus 3, 0. Yeah. So for example, if we take this one, this is diagonal parity 1, right? So what elements we need to include? For diagonal parity 1. Okay. What's this? D0 and D1 and B0, right? D minus B. So D1, B0. 1 minus 0, 1. So that's the element for diagonal parity 1. Okay. If we take this one here again here. So this is D2, B1. 2 minus 1, it's 1. So that again goes to diagonal parity 1. So that's how we take these elements. We consider these elements into diagonal parity. So what elements we XOR to get a diagonal parity? So that's how we get from this formula. D minus B, data blocks minus block. Okay. So that's what this slide explains everything about. Okay. So again, it's modulo calculations. So you just need to neglect the sign. Okay. For example, we have this one here. This is D3, D0, B3, right? D0, B3. D minus B. 0 minus 3, it's minus 3. So take the modulus, it's 3. So it belongs to the third diagonal parity. Okay. Any questions in the diagonal, how we consider the diagonal parity? It's simple XOR, but just use this formula to know which element contributes to which diagonal parity element. Okay. Next slide. Taking time. Okay. So this is how we done the calculations. Okay. So for example, if we lost 2 data drives, if we lost 2 data 2 drives of data. So how do we reconstruct it? We just have this data. So we need to reconstruct this data. For example, if we lost somehow. So it's simple. So for this is the one the NetApp people calculated, and they asked us to calculate the remaining things. Okay, so it's simple one, right? So we just lost this element right there, and we have every other element for this diagonal parity one, right? So we'll just XOR these three, and we'll get this one. Okay, so it's a decimal, so we'll just 12. And we'll just add these things, and we'll subtract from 12, and we'll get this number. That's it. So we're adding it to get this number. So we are adding these numbers and subtracting it from the diagonal parity to get this number. So it's 2 plus 2 plus 7, 11. So 12 minus 11, 1. That goes here. So how do we calculate the remaining things? Because in this stripe, we lost 2 elements. We can't reconstruct that one using diagonal parities. And for this diagonal parity, we again lost 2 elements. And for this one, we just lost 1 element, so we can just reconstruct this one. But we lost 2 elements in each of these things, so we can't reconstruct with the diagonal parity, with the use of diagonal parity. But we can do that with this stripe diagonal, right? So this is how we rebuild the things if we lost a complete D data drives. Okay, so that's what this slide explains about. And these are not the real elements, actually. Sorry, I'll do that. First, I'll explain and I'll do the animations. Yeah. D0 and D1 are failed. That's what we have just discussed. This means every right 4 stripe is dead. Every element in one diagonal parity stripe is dead, right? And DS0 is dead here. DS1 is degraded. I mean, it's we just lost 1 element. Degraded means we just lost 1 element, and we have just saw how to calculate that if we lost 1 element. And next, DS2 is degraded again because we just lost 1 element here. So how do we calculate this thing? Yeah. So what's the answer for this one? 1. Yes. So that's how we reconstruct if it was degraded. Yeah. People got it. Yeah. Diagonal stripe 3 is dead. Yep. So let's see how we rebuild that. So that was already rebuilt the thing. So come on. It's a little lag, so give it some time. Oh, yeah. Okay. 1, 3 from parity. Sorry, 1, 3. This one from the parity, because we have just calculated that's 1. So again, we can get this one, right? So we just, because it's how we calculated using these 4. Since we know this one, we can just know how to rebuild this one, and so on. It's easy now. You can just calculate this one using all the other elements from DS3. Again, you can do this one now. Okay, this one, because you now know how to all the diagonal stripes. So you can calculate this one again using diagonal stripes. You can calculate this one using the stripe. And this one again using the diagonal stripes, stripe, whatever. So that's how we rebuild if we lost 2 elements out of the matrix or out of the RAID. Yeah. So this is the double degraded volume. So how many diagonal stripes we have for this one? So the number of diagonal parities depends on the data drives. So how many data drives we have in this example? 2. So diagonal parities are 2. That's it. So number of data drives gives the number of diagonal parities. Okay. So how we reconstruct this? Which blocks are failed? We have like 4 blocks. Which blocks are failed? D0 and P. So D0 and P were failed. Those are the 2 data blocks, 2 blocks failed. So we need to reconstruct this thing. Okay. So which elements comes to the diagonal parity? So this is again, this is D, this is P, B, okay, B. So what's the formula? D minus B or B minus D? Anything. D minus B, anything works. Actually. Yeah. So yeah. So what's the first diagonal parity? First, let them answer. Oh, I just told them which blocks are failed. They can see there D0 and P are failed. Okay. So drive 0 block 0. That was failed. Drive 0 block 1, drive 0 block 2, drive 0 block 3. So the entire block, drive 0 block 1, 2, 3. Those are failed. And again, parity, I mean, drive 3, parity, yeah. Parity block 1, 2, 3 also failed. Or parity B0 is also failed. So those are the drives, those are segments that were failed. Okay. Now, how can we reconstruct it? Or what diagonal stripes are the drives part of? So we have this thing here, diagonal parity. So which elements contribute to the diagonal parity 0? That should be D minus B should be 0, right? So what are the blocks that contribute to DP0? Yeah, D0, DP0. So D0, B0, 0 minus 0 is 0. So that's the diagonal parity 0. And D1, B1, 1 minus 1 is 0. So that's again the diagonal parity here. I'll do that. So 0 and 0. So these two were here. And what's DP1? So now it's your turn. What's DP1? So which elements contribute to diagonal parity 1? Here. See, 1 minus 0, right? So D1, B0. What's this element? D1, B0, right? 1 minus 0 is 1. So that's diagonal parity 1. Again, this one. D2, okay, B1. 2 minus 1 is 1. That's again diagonal parity 1. So these two elements contribute to this diagonal parity. So we'll exert these two to get this one. We'll exert these two to get this one because D minus B for these two blocks is 0. D minus B for these two blocks is 1. So this is diagonal parity 0. This is diagonal parity 1. Yeah, so that's what it explained. DS0 because D0, B0 and DS0, it's again 1 minus 1 is 0. So these two contribute to this one. So 6 XOR A is this thing. Okay. Again, you know how to do XOR, right? So it's easy. Again, we have discussed these two contribute. So let's begin with DS0. Diagonal 0, B0, D0, B0, stripe 0, extend to 0, D0, B0, D. So again, these two contribute to this one and these two to here, right? I mean, this one is D0, B3, 3 minus 0 is 3. So this element, and again, this one, D1 and B0, 1, 2, 3, 3. So 0 minus 3 is 3. Yeah, it starts over each extent. So it's these two to here, and again, these two, I mean, these two to these two, okay? So that's just the extension. So we can get these two by XORing things first. Next, rebuild P0. That's again 2, 2, 3, 3. Finish with RAID 4, D0, B1, and D0, B3. Okay, that's how we reconstruct. Okay, that's just the simple XORs. XOR these two to get this one, XOR these two to get this one. XOR these two, I guess. No, 3. to get this thing, these two to get this thing. That's it. So that's the extension. So whatever the first row we do, that's the same thing we do for the next two rows to calculate the parities. That's it. So I guess you now know the answer why we haven't done the diagonal parity. We can go to the next one. 6 XOR A is C, C XOR C, 7 is B, C, B, C, B, right? C XOR 6 is A, 6 XOR A is C. And again, C XOR 7 is B. Yeah, so that's how we got these two things. And again, C XOR 3 is F. That's the stripe. So C XOR 3 is F and B XOR 9 is 2. So F and 2. So these are the elements we just reconstructed. Again, 3 XOR 2 is 1, 9 XOR 5 is C, so 1 and C. And it's simple. So that's how we reconstruct these bits. So you know how to, which elements contribute to diagonal parity. So we'll take those elements and XOR, and we'll take a stripe and XOR these two things to get the parity. That's it. Yeah. Use the diagonal parities elements to get the diagonal parity. Use the stripe to get the parity. Okay. Rate DP limitation. So before we go here, or we can discuss rate DP limitations. Diagonal stripes constrain the volume size. Okay, so we should have a fixed volume size to construct a diagonal parity. We just can't construct the diagonal parity with the number of drives number of blocks we need. Simple solution: if your user requests a non-multiple, shrink or grow the volume as needed. So if there are n data drives, each diagonal extent must contain n segments of data. Diagonal stripes. Oops. Could not. No. These wires, I just can't. If I mess up these wires, if I move these wires, it's stopping. I just moved these wires. Give it. Why? Let's just mirror it for a second. Let's see. What's the problem with the display? Or we could share that from the Teams, and you can share it on, or you can just join in Teams and you can just share it. We'll get it right here if you share. Again, sharing and sharing again.
You see my screen?
I can.
Okay, so we're going to do the rate.
You stop sharing your screen.
Why?
I know.
Oh, you want me to stop?
No.
Here. Screen. Go here. Come on. Right. If you pull this up on your PCs or laptops, you'll be able to see it. Let me just see if we can share this thing on here, if the monitor will come back. I think your MacBook might have glitched out or something.
Just move these things.
Just a little bit. Yeah. Yeah. I don't know. Yeah.
Oh,
Oh,
okay. Okay.
Um, so let me go ahead and just go back in the mirror real quick here. Let's see. Let's see. HDMI. Someone did something.
Wait.
See, right? Sorry. Yeah. Extend these displays. Um, I think the cable's come loose or something. All right, so everybody go ahead and sign on
Teams.
to Microsoft Teams real briefly, and we'll show you briefly how this works. It's the best we can do at this point. This is a function called RAID DP, or diagonal parity RAID. And similar to the RAID 4, it starts with the same code base. And I don't know if I have my microphone on.
Yeah, it's on. I can
It's on?
hear you.
Okay, good. You can hear me? Good.
Mhm.
Okay. So again, we dump drives. We have a pretty print drive. In this case, we have extra drive. We have a parity drive and a diagonal parity drive. Then we have initialize the data drives, and we specify how many drives we want to make and how many blocks we want to make total in the volumes, right? So we basically just go out there and build a two-dimensional array, number of drives crossed by the number of blocks per drive. And then we can initialize the data on those drives to different patterns, random numbers, incrementing numbers, and kind of a power number where each drive has 2 to the power of the drive number itself. Then we define a function called generate P, which we use to generate the RAID 4 parity. The only difference between this and the previous example is that we have a -2 on there because we've got, say, 6 drives in our volume. One of those is diagonal parity. The second is the RAID 4 parity. So the number of data drives is 2 minus the number of total drives, right? And our number of blocks is whatever the length of that first drive is. So we initialize the data on the second from the rightmost drive, which is the P parity. We'll fill that in. The next function is called generate DP, where we're generating the diagonal parity. And you can see we have a fairly complicated chunk of code in there. We first of all calculate how many extents there are, where the extent is 1 diagonal stripe. And then the next diagonal stripe repeats immediately after. A good picture. Yeah, do 6 drives. Yeah. See, I'm lazy. I draw a squared table and just say, imagine there's white lines between them, but he's make it there, make it. Okay, so anyhow, so for that, for each extent, for each diagonal stripe, we then count through all the blocks in that diagonal stripe. And we XOR that into a sum and plug that onto the last drive in the group at the diagonal block connected with that particular diagonal stripe. So it'll initialize it all up. And you can put print statements in, download this, and try to understand it by actually running the code. So let's go ahead and I'm going to run the code down to about the 4th or 6th cell there. So now we go ahead and say we got number of drives is 7, blocks is 10. We're going to use random. We're going to use actually the powers method of initialization. So we initialize a random number if we want to use the random, so we get the same stuff every time for the examples. And we initialize, and you can see that on drive 0, it's 2 raised to the power of 0 is 1. Drive 1, 2 raised to the power of 1 is 2. 2 raised to the power of 2 is 4, so on and so forth. So we've initialized every drive. P and DP are zeros now. Now we tell it to generate the P parity, and it fills in that P drive with the value 1F, which is all the bits on the previous drives, the data drives. Now we tell it to generate DP. And in the code, what we're seeing is we take 1, XOR 2, XOR 4, XOR 8, XOR 10. We XOR all those together, and on diagonal parity block 0, we get a 1F. Diagonal parity block 1, we start with that 2 on drive 1 block 0. So we get 2, XOR 4, XOR 10, XOR 8, XOR 10, XOR 1F. We add all those together in hex in XOR, and it gives us a 1. Okay, and so on and so forth. So you can run the math through there. If you've turned on the debugger, you can go up here into your Jupyter notebook, click on the little bug up there, it'll turn it red, and then you can actually view the debugger panel and actually watch it go if you set a breakpoint and step through it. Here's our function for rebuilding a drive using the RAID 4 parity. Same thing as we had on the RAID 4 example earlier in the class. We have a function for rebuilding a drive using the row diagonal parity. And you notice that is stubbed out. We haven't filled that in yet. You can have the concern that that's going to be a homework assignment in the near future. So now we're going to fail drive 2. And again, we can rebuild the drive just like we do to the RAID 4. And we'll just say it'll go out there and XOR drive 0, 1, 3, 4 in the parity and drop that under drive 2. Now we can fail the P drive. We can rebuild the P drive using the RAID 4 rebuild parity. It's just a regular parity drive. You add up whatever drive you want to, or you can rebuild the RAID 4 drive using the generate P function, which is basically initializing the parity drive, right? And then we have a failing and rebuilding the diagonal parity drive, which we can rebuild by using generate DP to rebuild in place. But the next question for you in the course is how would we actually rebuild if we had multiple drive failures? And so we might as well turn off the recording.
Fine, we'll just continue
Yeah.
recording.
Am I still recording? Am I recording?
Yeah. I'm
Okay.
recording.
You're recording. Okay. So I'll stop sharing my screen, I guess.
Yeah, I will stop sharing the screen and I will start sharing my screen.
And we'll do RAID RTP next time. We'll just take a brief beginning at the beginning of next class to do the RAID RTP for the Tuesday, Thursday. Okay. Team teaching. Yeah. So they said there's something funky about Jabara. Other buildings.
People can't really.
We're gonna
Mm-hmm.
supposedly get the network. Okay.
So,
Okay.
what is diagonal parity is 0?
That's fixed.
Which
I tried it.
Professor, you can just mute your camera. I mean, I'm muted. Yes. So now can you hear me? There. Now, yeah, you can hear me. Okay. Cool. So which elements gives us diagonal parity 0? Huh? Yeah, so which diagonal parities, I mean, which elements gives us diagonal parity 0? Yeah. Yeah, this one is 1, I mean 0, right? And this one is 0, and 2 minus 2, and 3 minus 3 uses the diagonal parity here, right? And we have a diagonal parity 1. So what are the elements that gives us diagonal parity 1? D1, B0, okay. Next, 2 minus 1, and again 3 minus 2, and this one 4 minus 3 use diagonal parity 1. And what's diagonal parity 2? Yes, D2 B0, 3 1, okay, and 4 2, and the next one 2 block 3, yes, right here 2 3, yeah, you get 2 2. Right here 3, and again 4 minus 1 3, right here 3 1 2 3 3, and 3, okay. And do we write diagonal parity 4? We have 4 data drives, we have 4 parity diagonal parity bits. So why don't we write 5 now? Because if we put like here 4 4 4 4, so where do we write our diagonal parity? Extend this, right? So there is no diagonal parity to write. It's right. Yeah, we'll use this number. Yeah. Oh, okay. Yeah, that works. Yeah, we'll just leave 4 right there. So sorry. Yeah, let's so you know how to calculate the parity here, right? So what's 0 XOR 1 XOR 2 XOR 3 in hexadecimal? Yeah, 0. Oh yeah. Oh, right here, yeah. It's 0. What's here? So 4 XOR 0 XOR 1 XOR 2. It's 1 plus 1 plus 1 1 2 4 7. What's 1 1 1? 7. So it's 7 right there. Okay. As you like. Okay. So what's here? 3 XOR 4 XOR 0 XOR 1 XOR XOR. So what? Yeah. Yeah. So what's here? 3. What's 3? 0 0 1 1. And what is 4? 0 1 0 0. What is 0? What's 1? Just XOR it. We have even number of ones. It's 0. We have odd 1, even ones. So what's this? 1, 2, 4, 8, 0, 1, 1, 0, 6. Put it right here. That's it. It's easy if you know XOR and you know how to convert it to hexadecimal numbers. And 2 XOR 3 XOR 4 XOR 0. Okay. And now, what's the diagonal parities right there? You XOR the diagonal parity 0 to get here. So that should be 0. Let's do it with green. Okay. So what's the diagonal parity 1? 1 XOR 1 XOR 1 XOR 5. What's 1? 0 0 0 1. What's 5? 0 1 0 1. So what's the answer? 1 2 4 4. Yeah. So that should be 4. What's the diagonal stripe 2? 2 is 2. 2 2 2 6. So what's 2? 6 XOR 2. Correct. And what's diagonal stripe 3? 3 XOR 7. Now we have calculated our parities and diagonal parities. So what if we lost 2 columns, 2 drives? Yeah. So what do you want me to erase here? 2 drives, any 2 drives. This one, 0 and 0, 1, 2, 3, 4. So we can delete any one of these drives. So which drive do you want me to delete? 2, this one? Okay. So and let's do one more thing. One more drive. One more drive. We can crash 2. 3, you said? 1, this one? Okay. What's the diagonal stripe 0? This one. This is 0. This is 0. This is 0 and this is 0. So how many drives or how many elements dead in diagonal parity 0? 2, right? So it's dead. It's not degraded. It's dead. So we just can't reconstruct these 2 using the other 2, right? So we can't do this one. So how many elements dead in in diagonal parity 1? 1, 1, 1. Yep, 2. How many dead in diagonal parity 2? This one, 2. This one is 2. What's the other 2? 2. And the other one? So we have like 2 dead, right? Okay. Is 2 minus 0. Oh yeah, this is 2. And what's the other 2? 2? 6 is 2. So yep, we have 4 elements out of which 1 was dead. So we know that this bit. So XOR 2, 6, 4, and 2. 2 XOR 2 XOR 6 XOR 4. What's 2? 0, 0, 1, 0. What's 6? 4. 4 is 0, 1, 0, 0. 0, 0, 0, 0. Oh, it's 2. Oh, what's 6, 0, 1, 1, 0. Yeah, the other 2 is dead. Okay. Two. So this element is 2. And the same way, calculate the rest. This thing right there, we can do that. So what's this stripe? Ah, so we have this stripe. So we'll just XOR these things to get this one. So 0 XOR 2 XOR 3 XOR 0 to get this one. 1. Now, what can we reconstruct next? Yes. D2, B1. So this we can reconstruct this one. How? 5 XOR 1 XOR 1 XOR 4. 4 are there, yeah. So what's 5 0 1 0 1? What's 1 0 0 0 1? What's 1 0 0 0 1? What's 4 0 1 0 0? What's the XOR? So it's 1. So we have reconstructed this one right there. So we can next reconstruct this stripe again, right? We can do that. Easy now. So 4 XOR 1 XOR 2 XOR 7. 7. What's 2? What's 1? What's 4? 0 0 0 0. Okay. So it's 0. So that's how we reconstruct things. So next, what can we reconstruct next? We got our 0 parity, diagonal parity. So 0 XOR 0 XOR 0 XOR 0, that's going to be 0 right there. Okay, we can reconstruct this stripe. 3 XOR 1 XOR 0 XOR 6. What's that? 0 0 1 1, 0 0 0 0, 0 0 0 1, and 6. What's 6? 0 1 1 0. 0 0 1 0. What's this? 4. Can just reconstruct this one. And what diagonal parity we can reconstruct now? Drive 2 block 3. Yep. So this one. Yes. 3. So what's 3? 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0. It's the XOR. We can use the stripe. So 2 XOR, 3 XOR, 0 XOR, 5. 2, 3, 0. What's 5? What's the? We have reconstructed it, right? So any questions? The reconstruction? Yeah. Yep. Okay, 12, 15, yeah. We can stop sharing. Can stop recording. It's time for quiz.